Hello everyone. Welcome to the discussion session on Würstchen, a novel architecture based diffusion model for text to image synthesis. So here is the list of contents for today's discussion. We're gonna go over the abstract of the paper that published it, and then we'll have a brief overview about diffusion models and their architectures. And then finally, we will get into the three-stage architecture of Würstchen. Finally, we're gonna wrap it up with some architectural details about the same, and then some example cases. All right. To begin with, version is a very new architecture for text-to-image synthesis, which aims to beat the current performance of state-of-the-art architectures with cost effectiveness. That is, in terms of the compute power that is used to train the model. It prioritizes both performance as well as computational accessibility. That is, it offers better performance than state-of-the-art architecture such as Stable Diffusion, and with very light computational efficiency in that goes in training the model. So
And
key
Pranav,
vision.
so it
Yes, sir.
is kind of during the inference also it is cost effective, right?
Yes, sir.
Yeah. Right.
So this requires less training time than expensive architectures such as Stable Diffusion, and which achieves not only competitive but also like superior results compared to these models. And one of the key contributions of this architecture is that it develops a latent diffusion technique, which learns an extremely compact semantic image representation, which is used to guide the diffusion process. In terms of numbers, the compression ratio is about like 1:42. So this is how compact that this model aims to achieve. All right. So before going ahead with the architecture, we're going to have a look at what are diffusion models. So diffusion models are a class of probabilistic generative models that are used for synthesizing photorealistic images. Of course, they are known for generating very high resolution images, and also they are known for their extremely good performance. But the downside is that they're very computationally demanding. For example, the Stable Diffusion model used about 150,000 GPU hours for training. So this is not feasible on any like personal computers. This requires a workstation compute powers in order to train such huge models. And this also, it's a known fact that higher resolution requirements implies a higher computational cost, which makes it more data intensive. So in order to combat all these drawbacks, the authors of Würstchen paper propose a three-stage architecture that is to tackle this problem using multiple stages and try to minimize the downsides by step by step. So the first stage, consists of training a text conditional latent diffusion model on a very low dimensional latent space. So this first stage is used to generate some extremely compact latent space representation, which is used to guide the diffusion process of another LDM, which is stage B. So this latent representation produces a latent image, which is in the latent space of another higher dimensionality of 4:1. And this latent representation is finally brought back to the image space using a decoder of VQGAN, which generates the full resolution output image of size 1024 cross 1024. So this diagram the whole sampling process of the three-stage Würstchen architecture. So, however, the training is performed in the reverse order to how the inference is performed. So, in during sampling, we first go sample from stage C. This sampled latent representation is used to guide the diffusion of stage B. And then finally, this latent representation is decoded by another VQGAN architecture in order to project it to the high resolution image space of 1024 cross 1024. However, the training is performed in the reverse order. We first train stage A, then we train stage B, and finally we train stage C. So yeah, this is the flowchart of how the training process takes place for Würstchen. uh, yeah. So the main takeaways from the paper is it has a novel three-stage architecture in order to obtain very extremely compact representation, as well as to facilitate training with very low compute power. And then it uses a text-conditional diffusion model in a very strongly compressed latent space that can achieve state-of-the-art art model performance at a significantly reduced training cost and inference speed. All right. So the first stage, that is stage A of Würstchen, it consists of F4 or of the vector quantized GAN or VQ GAN. So basically, this GAN projects it onto a lower dimensional latent space with a compression factor of 4:1. That is, it takes in an image, it learns to encode images of dimensions 3 cross 1024 cross 1024 into a latent space of 4 cross 256 cross 256. And again, it needs, since this is an encoder decoder architecture, this model first encodes it onto a latent dimension, and then finally again decodes it back to the image space. So yes, and when it is projected into the latent space, it learns to quantize it. So the network is must learn to reconstruct the image from these quantized latent representation. For example, the quantized latent representation is denoted by xq, which is given by the encoder part of the VQ GAN, that is f theta of x, and then the decoder part of the VQ GAN finally projects it back to the image space, that is f inverse of theta.
And Pranav,
And
is there any what is the code book size they chose in VQGAN? Is there any effect of it on results?
I'm sorry, sir.
So here there is a code book, right? Because they are operating in a quantized latent representation, right? In the stage A, that is a VQGAN.
Correct.
So yeah, what is the size of the code book? Is there any effect on the final
Yes, sir.
performance of this version architecture?
So the code book size is about 8,192, but I'm not sure about the effect of the size of the code book.
Okay. And the VQGAN here, the compression is 1:4, right? So it's
One is to
basically operating in the input to the VQGAN is 1024 and the output, the Latin representation is 256, right?
correct, sir.
Uh,
However, but during the inference or the sampling process, we use only the decoder part because we need the VQN only to project it from a latent space of 256 cross 256 back to the image space. We're not going to use the encoder part of the VQN.
during training, we will use both, right? But during inference,
Yes,
only decoder.
basically, yes, sir, because we need to learn not only the decoding part, we also need to learn how to encode, or like basically saying if we want to learn to decode it, we need to learn how to encode it into the latent dimensional space.
Yeah, that is only during the training. So
Yes,
otherwise, because during inference, we operate stage C and stage B, both are in the latent space only. So
yes,
when we move to stage A, there that is only the decoder part of it.
correct.
Right.
So in the stage B, the latent diffusion model, the main objective is to learn the latent representation that must be projected or decoded by the VQCAN. So this network is trained as a conditional latent diffusion model in the unquantized latent space of the stage A encoder. So for example, if we go to the diagram of the VQGAN, the encoder part of it first projects it into the latent time quantizer, converts into tokens, and then finally it is decoded. So this is the training process of stage A. However, when we are training stage B, we are not going to use the quantizer or the decoder. We shall use only the encoder part, and the training is performed in the unquantized latent space of stage A. And in order to guide the diffusion model, we shall use something called as a semantic compressor, which performs compression at an extremely high rate. That is, it first we compress an image of size 786 cross 786 into a latent representation of 1280 cross 24 cross 24. So this compressed latent representation is further compressed by using 1 cross 1 convolution. And this latent representation is used along with the text conditioning in order to guide the diffusion process of stage B. So finally, the output must resemble back the image that was downsampled by the encoder or encoded by the encoder. So the main purpose of the stage B architecture is to learn the latent representation that was generated by the encoder part of the VQGAN, so that when we are sampling, this will be easily decoded by the decoder part. Finally, the Yeah. All right. So the semantic compressor encodes the images of shape 3 cross 786 cross 786 into compact embeddings of shape 1280 cross 24 cross 24. We shall get the image size of 786 cross 786 by performing downsampling through bicubic interpolation. We shall first take an image of size 1024 cross 24 cross 3, and we shall interpolate it using bicubic interpolation in order to get a low resolution image of 786 cross 786 cross 3. And finally, we shall perform the semantic compression, which is used to guide the diffusion process. Yeah. The semantic compressor is basically an efficient net V2S backbone, in which it is initialized with weights that were pre-trained on ImageNet, and then noise is intermittently added to the semantic compressor's embedding, so that the model must not only learn to generate images when guided, but also it must understand what embeddings are kind of imperfect, as well as while sampling, in order to perform classifier free guidance, the text conditioning is randomly dropped during this training. Finally, we shall go to the training part of stage C. If we have a look at the diagram of stage C once again, so the main purpose of stage C is to learn the text conditioning part that was generated by the semantic compressor, because the semantic compressor is only used during the training part of the stage B model. But when during inference, the whole semantic compression part is replaced by the stage C model. So that means that stage C model must learn how the semantic compressor performed. So this is the reason we shall use the embeddings generated by the semantic compressor, perform noising on it, and then use it to train the model C. Basically, once the model is trained, it shall learn how to generate the same kind of embeddings that was generated by semantic compressor. When this is finally achieved, we can easily replace the semantic compressor part that was present during the stage B training by the stage C model itself. So in other words, we shall then be able to go from a very compact latent space representation of 16 cross 24 cross 24 all the way up to 1024 cross 1024 cross 3. So this ensures a compression of 42:1.
So in a way, the stage C diffusion model is there, right? So that
Yes,
is
sir.
kind of performing the role of the semantic compressor during the instance, right? So that's
Correct,
how
sir.
stage C is getting trained.
Right. So because when we were training stage B, there is no such as stage C. As a result, we shall use the semantic compressor in order to guide the diffusion process. Now, since the model is trained on these kind of semantic latent representations, we shall need another model which can generate this during inference time. So that is where the stage C model comes into play.
Hmm, hmm. Because we need those 24 dimensional embeddings during the inference. So those are
Right.
generated through model F theta, that is a C stage diffusion model, right? So
Right.
yeah, right. Yeah.
Yeah. So this is the whole training process of Würstchen architecture. Finally, when all the three models are trained, we shall go to directly to the sampling part of it. So first, we shall initialize a latent random noise of zero mean and unit variance, and then we shall perform sampling the sampling process for about tau c steps in order to get what is the very latent representation of dimension 16 cross 24 cross 24. Now this latent representation is concatenated along with the text conditioning and given to the in order to guide the stage B process. And then stage B again randomly samples
Pranav,
latent space
Pranav,
vector of size.
Pranav, can you go back to previous
Sir?
slide? Can you go back to previous slide? That sampling one.
Yes, sir.
So here, you are moving
Yeah,
from t to t minus one, right? So we need to recruit this one for tau c step. So is there any
correct.
closed form equation to get to tau c step directly?
So no, sir, this is the reverse process of the diffusion model since we have to go step by step.
Okay, so there is no closed form equation directly to go back in the tau c steps, right?
No, sir.
Oh,
So so we started off with random noise and then generated came to the latent space embeddings of the same size, which is now used to guide the conditioning part of the stage B. And again, stage B uses these conditionings and which starts off with a random Gaussian noise and then again performs the reverse process for about tau B steps. And finally, we shall have a latent space representation with of size 4 cross 256 cross 256, which is given by x tilde. And finally, this latent representation is decoded back to the image space of size 1024 cross 1024 cross 3 by using the decoder part of the VQGAN. So this was the whole sampling part of Würstchen. A simple architecture, but it offers like extremely compact representation as well as it is extremely efficient in terms of training the model. Since now instead of training on the image space, we shall be training in an extremely compact latent space. And yeah, some of the more finer architectural details about the whole Würstchen architecture. Coming to the stage B latent diffusion model, this consists of a unit architecture with four stages each in encoder and decoder part. The text conditioning for both stage B and stage C are applied from an unpooled clip H model with the embeddings having the dimensionality of 1024. And the semantic compressor is not trained during stage B. Since like initially I mentioned that it was initialized with ImageNet weights, but later on they came to realize that the ImageNet classes are not very exhaustive since they are like restricted to classify the weights are restricted to classify between the 1,000 classes of ImageNet. This is not very diverse. However, they are not trained during stage B. So here are a few more examples. Here are a few examples of the performance of Würstchen generated images. Uh, so that is about the Würstchen architecture.
but there is a nice interpretation, right, in the paper. If you have a paper, so could you please open it? Like, so in the page number 24 or 25, so
Uh-huh.
actually there is a nice interpretation about what stage C brings in and what stage B helps in. So it's like there is a nice interpretation, right? So do you have paper with you? Like, you
Yes, sir.
can,
I have the paper is having 29 pages with me, like the
yeah,
one
yeah,
I
you can
have.
open the 25th or 24th page. Yes. So there is a nice interpretation. So that
Sure.
I think that helps. So are you sharing anything?
One second, sir. I'll stop sharing the current screen and I shall share the paper. Just a second.
Sure, sure, please.
Sir, is the paper visible?
Yes, yes, yes. So, 24th or 25th, something like that. So there are, no. Can you go down? 25th के बाद,
Yeah.
there are certain examples, stage B and stage C. Okay, come down. Yeah, these are the examples. These are very nice. Like, suppose if you see stage
Yes.
C, right? So, and stage B,
Mhm.
suppose if there is only stage C, so it brings a semantic
Correct.
content, but the resolution, it's a blurred one, right? Low resolution. So stage B and
Right.
stage C. So both it helps in
Mhm.
bringing the high resolution information. So in a way, they suggested that the stage C brings the semantic content and sorry, stage C brings the semantic content and the stage B brings the those details. So it is a super resolution basically stage B performs. So
Correct.
in a way, this page is actually very nice about stage C and stage B and stage C interpretation.
Right. So does this also mean that it is better to, go from a low dimensional to high dimension in a stage-wise manner rather than directly going to the high dimension?
I guess so because I think incrementally it might help because when it comes to VQ gun, right? Again, it is a 1:4 compression, but that going stage wise maybe may not be helpful unless otherwise. Suppose if the VQ gun is compressing too much, so instead of 1 is
Right.
to 4, if it is doing 1 is to 16 there itself, then the stage wise might be helpful. But yeah, that is a bit of empirical we have to do. So analytically, I think it's a bit challenge to say, I guess.
Right.
Yeah, yeah. Thanks, Pranav. Thank you so much. So I guess
Sure, sir.
we are done,
Sir,
right?
any other questions?
So I don't have Sai. Do you have any questions?
A few, but like not at this moment. Am I audible, right?
Ah, no,
So
very
like
low
your
in
voice
value.
is very feeble.
Yes, and I'll plug in. Am I audible now? How is it?
Yes, sir, it's better right now.
Yeah. So I have a few, like, in context to this LDM that you were talking, right? Like about this compression ratio. So
Right.
maybe that if you can, like, explain that bit later, right? Like exactly what exactly is happening.
Yes, sir. So the target dimension that was to be generated by this model is 1024 cross 1024 cross 3. However, we start sampling from a dimension of 16 cross 24 cross 24. So the ratio of the scaling is 42 is to 1.
Okay, like so generally, so I've known stable like diffusion models, right? Like so
Mhm.
generally, what happens is you take like given an image or given an image or like something, right? So you convert that to an embedding using like let's say you have some architecture that you preconceived. So you convert
Right.
that to embedding. Let's say an embedding is of size like 809 or like let's say 4096 vector, right? Now
Right.
you're saying you will compress that to like very low latent space. Like let's say you are compressing that 4096 to like let's say maybe 128.
Uh-huh.
Is that what you meant when you said compression ratio?
Yes, sir. So, like instead of the original, like the whatever training we are performing, that is performed in this very low dimensional space. We are not performing in the actual high dimensional image space. So, this is an example of what is known as the encoder decoder kind of diffusion model. There is another alternative to these latent diffusion models called the upsampler based architectures. So basically what they do is they learn representations in low resolutions, not low latent dimensions. Instead of latent dimensions, they learn in a very low resolution space, and then we must use another model in order to upsample it back to the high resolution space. So this, on the other hand,
Okay.
tries to
So
learn
that
latent
is
representations.
earlier diffusion models were using stable diffusion, I think, is of this thing, right? So it generates some like 256 or 256 image, and then
Examples of the upsampler architectures are like unclip, imagine from Google, etc.
right.
So yeah,
Okay. So here,
so in order to
high
sum,
resolution is achieved using a like additional VQ technique, right? On top of
sir, like here we are not going from a low resolution to high resolution. In fact, we are going from a low dimensional latent space. Because in the if you go into the low dimensional space, the whatever samples that are generated, they don't even resemble images. They are just latent representations. However, on the in case of upsampler based architectures, if you closely look at the images in the low resolution, they also look like images itself. We just need another network to kind of bring it to a higher resolution space. Here we are learning in what is known as the latent space.
And
And in
Pranav,
fact, in this
actually,
architecture,
we can navigate this question
okay.
through that how the architecture this one differs from the stable diffusion. So that way we can exactly clearly bring out that difference, right? So suppose if we go to that diagram, right? So what are the component extra we are bringing in into this one? So
okay,
that
so
from that way
I'll
we
just
can easily, I guess.
right.
Because Sai was, I guess he's asking exactly what is the difference between the latent stable diffusion model and this, right, Sai?
Yes, Prem, yes.
Okay, so if I go to the diagram again, okay, uh, yeah, oh, this is the training. Yes. So, so the main difference between a stable diffusion and this architecture is that it has the most basic difference is that it has three stages. So we have stage one, one of the stages which works in a low dimensional space, and in fact, this is not kind of decoded or anything. This is used to guide the diffusion process of another model, because we are not giving the latent representation to the as input to the model. In fact, we are using it to condition the second model, and finally we are using another decoder architecture to bring it to the original image space. This could be, yeah, one of the differences that we can see compared to stable diffusion.
Okay. Got it.
Because in the standard stable diffusion, right? So the unit part, that is stage B, is the one which is trying to generate image in the latent space through a text conditioning, right? So, but when it comes to in this one, right? So most of the semantic content is generated in the lower dimensional space by the stage C itself. So stage B, simply it is trying to bring out a lot of details. So most of the reconstruction is going to happen in the stage C, which takes very less compute because it is operating in the 24 dimensional space. Whereas stage B, which is operating in the 256 cross 256, so it requires less number of iterations to converge. So that's where the compute, right? So overall computation, that inference time would be much lower than the stable diffusion. I guess uh, is it addressing that one, Sai?
Yeah, yes. Right. Yeah. Yeah, I think I've got a basic idea. Like I think I'll go back and probably understand more.
Sure. Thank you, Pranav. Thank you so much. So for
Sure,
presenting
sir.
this.
It was a pleasure.